So we'll be talking frequency response. So we did the time response already. So how to convert your S to time domain, right? Time domain T. That's the inverse Laplace transform, right? S to time domain. Time domain to time domain to S domain. Time T S domain is the Laplace transform. Okay. Transform. Now we'll be doing S domain to frequency domain now. S domain to frequency omega domain, right? That's what we'll be doing. So as you know, this S equals sigma plus j omega, right? Okay. So this omega is the frequency. Now what we'll be doing here is this. So what we're trying to do here is, how does the system respond to sinusoids of different frequencies? Now here we'll be just talking about sinusoids. Sinusoids. So what I meant by that is, so we have the curve, input curve like this, sine function, right? Sinusoid means sine function. That's your input. Then this input is fed to the system. This is our system. When sinusoid is fed to the system, then how does the system behave? Again, this is for the steady state, okay? System in steady state. If the system is in steady state, then the sinusoid input, this is the sinusoid input. The good news is that the output is also sinusoid. That makes our life too much easy. Not only sinusoid, it's the same frequency. How cool is that? Same frequency also. Same frequency of this guy. But what's the difference then? Output sinusoid, frequency same. Then what's the difference? The difference could be in amplitude and phase. That these two things could be different from input. Okay. So that's what we'll be talking here in this frequency response. That's what we'll be talking. Now, let's say let's say the system represented by transfer function G, right? This is your G. Now, sinusoid, how do you represent the sinusoid? Sinusoid is represented as, let's say your input is represented like this. So your input is in sinusoid. How do you represent sinusoid in complex notation? Can you help me? How do you represent sinusoid in complex notation? E to the j omega t. Remember, sinusoid means sine omega t or cosine omega t, right? In complex notation, we can write like this. So then what happens what is the frequency response of this? Frequency response in this case is, if this is G, then your frequency response is, see, it's also sinusoid, right? That's what I said. The output is also sinusoid. Okay, if input is sinusoid, The output is also sinusoid. Okay, with the same frequency. See, omega also same. This is omega. This is also omega. Exactly same frequency. But the difference is the amplitude. How do you represent the amplitude? Here the amplitude is 1, right? See, there is nothing means there is 1. Now here the amplitude will be different from 1. So how do you find the amplitude here? This amplitude is somehow related to this function here. Okay, so this amplitude is given by or is a function of j omega, meaning this guy does not depend on t. See, this input is function of omega and t, right? But this g, which is amplitude, is just a function of omega because it doesn't depend on time. That's cool because omega is constant, right? Omega is constant. Suppose you have some inputs, you send the sinusoid input, which has constant frequency, then this guy does not change. That's the good news. As long as, so frequency is constant. Okay, this is how the system behaves. This is called frequency response. Question here, please. Sometimes we write this G as like this. Sometimes we write like this also, G e to the j omega also. Either way, it's the function of omega, right? J omega, okay? Question here. So now let's talk about this guy now. This is the amplification. This is the amplitude, right? This is the amplitude of the output. So this G j omega, I'll be talking about this guy now. This G j omega. So what is this is complex number, right? This function is function of j omega. Okay, this is complex number. Now how do you write the complex number? Euler. What is the complex number? How do you write a complex number in Euler notation? A e to the I phi, right? Suppose your complex number A tilde is 2 plus 3j. Then what is your A? A is square root of 2 square plus 3 square. See that? Then what is your phi? How do you find the phi? Phi equals inverse tangent 3 over 2. This part, the part with the j over 2. That's what you do, okay? That's how you find your A and phi. This is your A. Okay, this guy is your A. A magnitude, and phi is, this phi is given by this equation. This formula rather, okay? So similarly, how do you represent your G j omega? So in the same way, you can represent your G j omega like this, e to the e j omega. Let me write e j omega. Or if you want, because we have your complex here, you can write like this too. E to the j omega, okay? Let's keep it like that because that explicitly tells us that is complex notation, right? Okay, so e j omega. Then that's the A magnitude. Then what is the phase? Phase is e to the minus I. Sorry, I keep on writing I because I'm so used to using I in physics. And this is engineering, okay? That's the thing. I keep on forgetting. So J, then angle. What is the angle? So we don't know what is inside Z, right? So A plus, JB, I don't know. I don't know how does this J look like, okay? That's why I don't know what the real and imaginary part. That's why I simply write J angle of G. That's what I do. Hope it doesn't confuse you a lot. So where this guy is, suppose this guy is A plus BJ, then when I say angle G e to the J omega, what I meant is this is exactly inverse tangent B over A, okay? This guy can be written as this, which is this. Does it make sense? Okay. Now, what does your output become then? What is your output? Help me here. What is the output then? If you have your G, J, omega, what is your output? Your output is CT equals G, J, omega, or e to the j omega, whatever you call it, j omega, then e to the j omega t, right? That's your output. See that? That's your output. Now plug this in, this guy here. Plug this guy in here. Okay, then what do you get? G e to the j omega, e to the j, and this guy has j omega t, this guy has j angle g, right? So can I factor out, help me here, can I factor out j? So omega t plus angle g e to the j omega, okay? This notation looks vague, but it's very simple, okay, if you understand it, okay? Now, so this guy in short also can be written, this is actually can be written as mg, magnitude of the, this guy is written as mg, this whole thing, mg, and e to the j omega t, and this guy in short can be written as simply phi, plus phi g actually, phi g. See, this guy can be written as mg e to the j omega t plus phi g. Guys, any questions so far?
Nope.
Okay, so what do you see here? What is the phase? What is the amplitude here? 1. Now what is the amplitude you got here? Mg. Amplitude is changed by mg. Mg times, right? 1 times mg. Amplitude changed by mg. Then what is the phase here? Phase here is omega t. What is the phase here? Omega t plus phi g. What is the change in phase? Amplitude change and phase change is phi g. This is called amplitude response. This is called phase response, or you can call magnitude response also, okay? Magnitude response. And this is also called phase response. And if you combine these two, then we call it frequency response. There. That's what we'll be talking in this course, in this chapter. Frequency response. That's what we'll be talking. Okay. In other words, this guy is frequency response. Okay. This guy is the frequency response. This guy is the frequency response. This guy has two parts. One is magnitudes, which is mg. The other part is phi g. This guy is called frequency response. It has two parts. One is the magnitude, the other one is phase, mg and phi g. That's called frequency response of frequency response. Yeah.
So that equation on the bottom that you wrote, mg times e to the j of wt, is that wt times phi g or plus?
Sorry.
Okay, thanks.
Yep. Wt plus phi g. Okay, I'm just rewriting this guy.
Yeah, that's what I thought. I just didn't know for sure.
Yeah. Okay, so that's what we'll be talking in this course. Now, as you remember, if you remember, we this is the slide from previous lecture. So when I was talking Routh-Hurwitz criterion, then I put the slide over there. So we had a plan to cover all those things. We did this Routh-Hurwitz already. We did this root locus plot. Now we need to do Bode and Nyquist. That's what we'll be doing here in this lecture. We'll discuss Bode diagram and Nyquist diagram. Okay, let's summarize. Okay, let's summarize what I did before here. Actually, this is what I did before. Okay, all right, let's summarize what I did here is how do you find, if you are given, this is the summary. This is called frequency response function. Frequency response function, FRF. Mg along with, this is not less than, okay? This is not less than mg and angle phi g together. That's called frequency response function. So how do you find the frequency response function? This guy is this guy here. This guy is this guy, okay? This is same guy, which is also written as this. It means these are exactly same. Suppose you are given GS, right? Then how do you find the JW? That's the conclusion of this discussion so far. If you are given GS, how do you find frequency response of this GS? It's very easy. Simply change your S to JW. It's that easy. That's what we figured out right now. Okay, see that? So if you are given GS, your frequency response is this. If your system is GS, frequency response is this. Meaning, you simply change your S to J omega. It's that easy. Mathematically, it's that easy. Okay, so we'll be doing, yeah, this is the linearity property. So if RT is alpha 1, so we just did only one here, right? Our RT was this. Now, suppose you have a RT, the combination of different frequencies like this, omega 1 and omega 2 in this case. Could be 3, 4, 5, as many as you want. So if you have the combination of frequencies like this times alpha 1 and alpha 2, which is called linear combination, by the way, right? Then if this is your RT, the input, the output will be also linear combination. But it will be slightly different because here, in here, you just add G here. You just insert Z. Okay? Similarly, here also you insert Z. Everything else will be same. Okay, even though you have combination, linear combination of different frequencies, then output also found accordingly. Okay, that's the beauty of this method. All right, let's do this one by one. Okay, now first of all, we'll be doing Bode plot. So then we'll be doing the Nyquist plot. So what is Bode plot? Bode plot is, remember we had a G, J, omega. What is your CT? CT was G, J, omega times e to the J, omega t. Given that your RT is, your RT it is J, omega t. If your RT is this is your output. Now, we'll be plotting this guy here only. Frequency response function. This is the frequency response function, right? So take the log of this guy. Take the log of, because this guy has two parts, right? One the magnitude, the other one is phase. Magnitude also can be written as G, J omega in this way. Okay, and phase also can be written as angle G, J omega. If you plot this guy versus log frequency, log of omega versus log of omega, you plot the magnitude versus log of omega and also the phase versus log of omega. These two plots altogether are called Bode plot, discovered by the engineer whose last name was Bode. Okay, so I'll show his picture in a little bit. Okay, in a few, after a few slides. So these Bode plots are simplest tool for visualization and synthesis. So instead of actually, you know what? Instead of doing this guy, we do this like this, 20 log G. Okay, we also take log here. Okay, instead of doing simply G or simply mg, instead of doing, okay, let me read that. Instead of doing mg versus log omega, we rather do 20 log mg versus log omega. Okay, we do the mg, but in this form. So when you do in this form, this is called decibel. Okay, this is the definition of decibel, meaning you want to have the unit of mg to be decibel. That's how you change your mg to decibel unit. dB, D-E-C-I-B-E-L. Okay, decibel versus frequency, radian per second, right? Okay, frequency radian per second. So this is how you do the plot. This is your decibel. This is your radian per second. Okay, and you'll see some kind of plot. That plot is called Bode plot. And they are useful for visualization and synthesis. Similarly, we have the another plot that we'll be talking about in this lecture, in this chapter, is the Nyquist plot. Nyquist plot, also called polar plot. Okay, Nyquist, the polar plot is invented by the engineer Nyquist. That's his last name. So that's why we call either polar plot or Nyquist plot. And what does that polar plot look like? What you do here is we plot the J omega again. We plot the same frequency response function. I know this is complex, right? This guy has the real and imaginary part. Okay, imaginary part. In the Bode, what do? In the Bode, you write G in terms of mg and phi g. And you plot both of these. That's the Bode. However, in the polar, what you do is you write G as A plus Bj, like this. Instead of writing mg and phi g, you write G in another form. Sorry, different form, right? So meaning A plus Bj form. And where A is function of omega, let's say this A is function of omega, let me write this explicitly. A is function of omega and B is also function of omega. Okay, then what you do is you plot real and imaginary. You have the real axis here, real part, and you have the imaginary here. Okay, and for some particular frequency, you have AB here. For another 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 frequency, you have AB here. So you get different points like this, right? This is called Bode, polar plot. We'll do this in detail. I have a solid example for that. Okay, this is just the introduction for now. Guys, any questions so far? Guys, please ask anything. Comment, please.
Think I'm okay.
Okay, very good. All right, let's do the Bode. Let's just start with the Bode plot, then we'll move on to the polar, okay? Let's do the Bode plot in detail, little bit more detail, not so much detail because we don't have time. So a little bit more detail. Now let's do the Bode plot. I want to do the very simple function, okay? Let's say my system is, what is the frequency response of my function? Okay, this is my input, RT. This is my output, CT. My function is G. I have taken my G to be very simple. You cannot find simpler than that. Simply S. My GS is S. My G of S is very simple function, which is S. If you want to plot this function, meaning the Bode plot, then what do? What is Bode plot? Bode plot meaning find the magnitude of this guy, which is mg, and find the phase of this guy, phi g, and plot this guy as a function of log omega, and also plot this guy as a function of log omega. You have two plots. Bode plot meaning, actually I should have said Bode plots actually. Okay, there are two plots together. So function of, this is one plot, this is another plot. Both of them are called Bode plot. That's why, let me make the table. So when you plot the function, what do? Suppose you have y equals mx plus c, or b, whatever you call it. So suppose y equals 5x plus 3. Then how do you make the plot of this x and y? I mean, how do you make the plot of this picture, this equation? You choose x some value and y is different value, right? Choose some random value of x. X equals 0, what is your y? 3. X equals 1, what is your y? 8. X equals 2, what is your y? 13. Like that, right? In the same way, we do the same thing here. So you have the G. What is the magnitude of G? Your G is simply S, right? Your G is simply S. Let me choose some bright color. My G is simply S. So what is the magnitude of S? Help me here, because I have to find the, if my G of S is S. Now how do you find the frequency response from here? Frequency response is J omega, right? What is your J omega? J omega is J omega. Look at that. Now what is the magnitude of this guy? What is mg and what is phi g? What is the real part here? Real part is 0, right? 0 plus J omega. So what is your mg? Mg is real square plus imaginary square. 0 square plus omega square equal to simply omega. That's your mg. Mg is omega. What is your phi g? Help me here. Inverse tangent. inverse tangent omega over 0, right? What is omega over 0? Infinity. What is inverse tangent of infinity? 90 degree. Okay, so this is constant. Phi is constant throughout, 90 degree all the time. It does not depend on omega. I take the different value of omega now because mg is omega, right? So I take omega equals 1 here. When omega equals 1, what is your mg? Mg also 1 omega, right? See, mg is also omega. When you take omega equals 1, then mg is 1 because they are equal. Look at that. They are equal here. When omega is 10, then mg is 10. When omega is 100, mg is 100. When omega is 0.1, mg is 0.1. When omega is 0.01, mg is 0.01. Okay, so that's why my S is j omega, j1, j10, j100, j0.1, j0.01. Now, but the thing is, when you do the Bode plot, then what you have to do is you have to change this mg to decibel, right? dB. How do you change it to decibel? Multiply this guy by, take the log of this, log 10, then multiply by 20. That's how you change it to decibel. That's what I did here. This is my decibel. So then what is the decibel of, what is, if the mg is 1, then what is this guy? Log of 1, 0. Okay? When mg is 10, put here 10. What do you get? If this mg is 10, then what do you get? 20 log 10. Log 10 is 1, simply 10. Sorry, 20 decibel. Then when mg is 100, then your decibel value is 40. When this is 0.1, it's negative 20. When this is this, the value is negative 40. Then how about 5G? 5G is always same, right? See, it does not change. It's constant. Means 90, 90, 90, 90, 90 everywhere. Guys, question here.
So far, so good for me.
Nice. Okay, now let's do the other. So let me copy this table so that I can plot the graph. Now I have the data ready, right? Now I need to plot this guy with log omega, log of this, right? Log of this omega. Actually, this is in yeah. I'll show you how does the log scale look like. And I have to plot these two guys now. These two guys. This is plot 1, this is plot 2. We'll have the plot 2 plus together. Let's do this one first. First do the magnitude, then we'll do the phase, okay? Look at that. So let's talk about this guy. Now, first of all, I want to talk about the log plot. Remember we say log omega? So what does the plot look like here? The plot looks like this. You increase. In the case of regular plot, what do? You go 1, then 2, then 3, then 4, then 5, like that, right? But in the case of log plot, instead of increasing by 1, 2, 3, you change by only 1, right? Instead of change by 1, you change by times here, okay? This is 10 times. This is 10 times. 10 times 0.01 is 0.1. 10 times 0.1 is 1. 10 times 1 is 10. 10 times 10 is 100. That's how you do it. And this kind of scaling is called log scale. That's why we call it log omega. Does it make sense so far? This is 1, this is 2, this is 3. This is a regular plot, right? But this is log plot. This is log. In a regular plot, you can divide this guy into 10 parts, right? 1, 2, 3, 4, regular, exactly same. All of them are spaced exactly same. and the regular plot. Okay, these are exactly identical. Okay, I don't know. The space between these two points is exactly same as space between these 2 points. The space is exactly similar here. But in the case of log, see the spacing? The first spacing is very big one. Look at that. First spacing is very big, and second spacing is smaller. Look, this is second spacing. This is third spacing. Then fourth spacing. This is fifth spacing. Spacing goes on decreasing. Look at that. That's the thing. That's the property of log plot. Unlike the regular plot, the spacing is not same. They're different. Question here. Okay. Now let's plot the data now. We have the data ready. Let's do the plotting. Okay, let's begin with 0.01 here. 0.01, I started with 0.01 here. Then what is the thing? Negative 40. This is my negative 40, okay? Negative 40 dB. What is my next one? 0.1. When 0.1, my magnitude is negative 20. 0.1, magnitude is negative 20. Then 1. Let's do this one here. Then the magnitude is 0. 1, magnitude is 0 here. Okay. Then the next one is 10. 10 is where? This is 10. 10 is 20. 10 is 20. Look at this. Then 100. You have 100. The 100 is 40, right? 100 is 40 here. This is all decibel, dB. Does it make sense? That's one of the Bode plots. Now let's find the slope of this Bode plot, because this looks like a straight line, right? This looks like a straight line. Look at this. Now what is the slope of this straight line? Well, how do you find the slope? Delta y over delta x, right? That's the slope. Now let's try to make an angle here. So what is the delta y here? What is this delta y? Delta y equals, how much is this guy? 0 to 20. 20 minus 0. 20 decibel, dB. And what is the y here? Sorry, what is the x? X is from 1 to 10. That's called decade, okay? That's called decade, per decade. So divide by, so this is 1 decade, right? So that's why, that's the unit of this guy, 20 decibel per decade. That's the unit, that's the, help me, slope of this Bode plot. Now we did the magnitude part. Let's do the phase part. As you might have already expected, phase part should be easy, right? Because for each of them, this phase is same, 90, 0.1, 90, 1, 90, 10, 90, 100, 90. It's the same all the way. Guys, question so far? So far, so good. Let's do one more example. Now, in this case, we did the table thing, right? We use the table. This is very, preliminary way of finding Bode plot. But there is some quicker way of doing it, okay? So the quicker way is called, the method called asymptotic approximation. By using this approximation, we can make the Bode plot quickly. Okay, let's do that, okay? To understand the asymptotic approximation, you have to understand the corner frequency, first of all. Okay, corner frequency. All right, so let's say, suppose you have a function g, this guy, right? We are talking about this function, right? We have to plot this guy. So when omega tends to 0, let's say this function behaves like this. When omega when omega tends to infinity, let's say this function behaves like this, right? This is just an example, okay? You have a function j omega. This is the function. Now I'm trying to study two extremes. One is when omega tends to 0. The other is when omega tends to infinity. Let's say when omega tends to infinity, this guy behaves like this. Omega tends to infinity. And on the other hand, when omega tends to 0, this guy behaves like this. Then what happens in between? Between 0 and infinity. Maybe this guy goes like that, this guy comes down, they meet somewhere, right? They meet somewhere here. The frequency at which they meet is called break frequency, or we can also call corner frequency. Okay, remember Bode plot can have more than one corner frequency. Okay, you can have the Bode plot like this, like this. You have one corner frequency, two corner frequency, three corner frequency, four. You can have more than one. The one thing is that, so at the corner frequency, so whether you find this point based on this approximation or this approximation, at this point, you should be able to find this point by using either of them. This approximation at this point and this approximation at this point should give you the exact same answer at the corner frequency. So first of all, if you want to use the approximation method, then first step is to find the corner frequency. Does your Bode plot have corner frequency? That's the first thing you have to figure out. So how do you find the corner frequency? So in this case, I'm going to do the Bode plot for this guy. Do I have this corner frequency for this guy? So how do you do that? So s plus 1, what is on the denominator? Oh, you don't have anything on the denominator, right? So s plus, so you just have the, if you set it to 0, you get s equals negative a. Okay, this a is the corner frequency. Remember the pole, in this case 0, right? In this case 0. So the corner frequency are the zeros and poles of the transfer function. Zeros and poles are the critical or break frequency. We also call critical or corner or break frequency. Guys, question here. Guys, any question, please? Hello. So far, so good?
I think I'm okay so
All
far.
right. Okay. So I made a mistake here. So it should be s plus a, right? So s plus a. So that's why it should be j omega plus a. Okay. So this is a typo. So s equals j omega plus a. Please do that. So now, so I have to change, since my gs, that's what I meant, gs equals s plus a, my g j omega, which is the frequency response function, will be j omega plus a. I want to rewrite this guy. Can I write this guy like this, a and a? So this a factor out. So what do you get? A j omega over a plus 1. Okay. So now let's find the two extremes of this guy. So g j omega, right? Let's find the two extreme of this guy. When omega tends to 0, how does this guy behave? This guy behaves as, this guy becomes 0, right? Then simply get a. Your g is a. Okay. So that's what I did here. Your g is a, which is a plus j0, right? Okay. Now what happens? What happens to the magnitude of this guy? Because remember, we need the magnitude and the phase for this guy. What is the magnitude? Mg. is A. What is the phase? Phi G. Phi G is inverse tangent 0 over A, right? Inverse tangent 0 over A. Because my Y part here is 0, X part is A. So that's why this is 0. So phi G is easy. Phi G is always 0. How about mg? Mg is A, which is constant also. Now let's do the infinity, right? So we know this is my G response function, right? What happens at infinity? Meaning omega is much greater than A, right? That means omega tends to infinity. Okay. Then when this guy is much bigger than A, this guy is very big as compared to 1. So this 1 can be simply ignored, right? We can simply ignore this 1. So that's why my Gj omega becomes simply this guy. That's what I meant. Then you can rewrite this guy as now what is the angle? Okay, we found the magnitude. This is your function, right? What is the magnitude of this function? Help me. What is the mg of this function? This A and A cancel out. Magnitude is simply omega. See, it's exactly like before. See, we have magnitude A here, right? Look at that. Magnitude omega here, right? In this case also. See, magnitude was omega here, right? It was omega in the previous example. It happens exactly same thing here. But this case is for the infinity, right? Like meaning the higher end, not the regular one, okay? So this is the high, this is the asymptotic approximation, right? For the high frequency, that's what I meant. High frequency, it exactly behaves like previous. Then what is the angle? Mg is omega. What is the angle phi g? Because your real part is 0, right? 0 plus. If you don't have anything, means you have 0. 0 plus something something j omega, that thing. So that's why something over inverse tangent, something over, that's your phi. Actually, this is j, right? This A and A cancel. Sorry, this is omega, right? A and A cancel. This is omega over 0. It means your phi is 90. Phi is easy. Okay. So this is the conclusion. If you take a look at the magnitude, at the low frequency, what is the magnitude? Magnitude A. At the high frequency, what is the magnitude? Omega. Again, at the low frequency, what is the phi? Phi z. Can you remember from the previous? Phi g is 0. And in this case, your phi g is 90. Look at that. Now, what is the breakaway frequency? Break frequency is A, right? Omega equals A is the break frequency. Meaning, two asymptotes meet at the break frequency. From the lower end and from the higher end, they come and intersect at omega equals A. Let's do that. So here, let's do that. So lower end. So let's talk about lower end first. This is the lower end, right? Let's talk about lower end. For the mg equals how much? Mg equals, for the lower end, mg equals A, right? Mg is A. So what is the mg equals A, meaning what is your 20 log mg then? It will be 20 log A, right? That's what I meant. For the lower end, okay, for the lower end, you get the Bode plot like this. What is the angle? Angle is 0, meaning Bode plot with the angle. Bode plot in the lower end, you get like this with the angle 0. See, angle is 0. The lower end. Let's call this is the lower end, okay? This is the lower end. I will call this is the lower end. In the lower end, magnitude is 20 log A and phase is 0. How about the higher end? Higher end, let's talk about 100A, right? Remember, at the higher end, your mg is omega. What is your 20 log mg then? 20 log, help me here, 20 log omega, right? Remember, your omega is 100A, 100 times A, okay? That's why when your omega is 100 times A, what do you get? 20 log 100 times A. So how do you rewrite this guy? Can I rewrite this guy as like this? 20 log 100 plus 20 log A, log property. Can I, this guy is what? This guy is 40. 40 plus 20 log A. That's it. 40 plus 20 log A. There. Look at this. Similarly, you can do 10A. You can get this point. So this is the higher part. This is the lower part. We found this much, but we haven't found this guy yet. So similarly here, for the higher part, what is the phi? For the, higher frequency, what is the part? What is the angle? Angle is 90, right? 90, this is the 90, look at that. This angle is 90. So we got the higher, at the higher frequency, your Bode plot looks like this. At the lower frequency, you have your Bode plot looks like this. Similarly, higher frequency, lower frequency, Bode plot looks like this. This is for the magnitude, this is for the phase. How about something in between? Now you have to guess. Something in between you have to guess. Okay. All right. So what is the, now think about what is the break frequency? A, right? A, until A, they don't change. They change at A only. That's why by the help of break frequency, we assume that, okay, since this is break frequency, there is nothing change here up to break frequency. Since this is break frequency, there is nothing change, it comes like this. There. By the help of this break frequency, we can fill in the blank. Similarly, we had this here, right? So what do you think this guy at break frequency is A, right? Look, break frequency. How do you fill this in here? Do you continue this way? This way? They never meet. They are supposed to meet, right? At break frequency, they are supposed to intersect. So then what do you think you should do in between in this case? Remember, this is a break frequency, they should meet. Looks like they go like this, they come down like this and meet. Does it make sense? Guys, make sense?
So I think I kind of get it for the top one, but I don't know about the bottom one. If we...
Okay, so you understand this part, right? Low part and high part?
Yeah, but I mean, I don't know, like, because of Zoom, it's cut off at the bottom, but...
Oh, this one here?
Yeah, I can't see anything.
This is your A, this is your 0.1A, this is your 10A.
Okay.
This is your 100A, okay? I'm
right,
sorry about
so
that.
Why does it change at 0.1A and at 10A?
No, it could be here up to here also, okay? It could be here up to here. This is just the approximation, remember?
Okay.
Okay, this could be this also.
All right.
The higher end could come up to here. The
But-
lower end could come up to here. But the thing
Okay.
is, they have to meet here, right?
Meet there. So it's not really about what it looks like in between, like the high and the low, and then the A. It's just that they come together at A
Exactly.
is the main point.
Yeah, this is the approximation, right? It could be this or this. We don't know. But something like that. Does it make sense? Did I lose you?
Sorry, I'm just trying to write things. So.
Oh, okay, that's fine.
But yes, I think that helps.
Okay, good. Now, if you do the, in the where Octave, then it looks like this. Okay. Let me quickly do the Nyquist plot, and we are done. Okay. All right, let's do the Nyquist plot here. So I'm going to do the Nyquist plot for the function g cos 1 over s plus 1. Okay. So Nyquist meaning what? Find the real and imaginary part, right? So how do you write this guy in real and imaginary form? This is your GS, right? Let me write this down. GS is, this is the transfer function I chose. So what is the real part? How do you change the frequency response function? This is your frequency response function, right? Simply replace your S by J omega. That becomes frequency response. This is your transfer function. This is your frequency response function. This is your TF. This is your FRF. You simply replace S by J omega. That's all. Now this guy, find the two parts of this guy. What do I mean by two part? A plus BJ. Find A and B, because this is complex, right? Find A and B. But how do you find the A and B of this guy? Help me. How do you find the A and B of this guy? Do the complex you have to have the J on the top, right? Remember? Because your J on the top here. There is nothing on there is no J on the bottom here. A plus BJ. So bottom is 1. A plus BJ. Denominator is 1. That's why this J has to somehow go to the top. How do you do that? Do the complex conjugate multiplication, right? J omega. 1 minus J omega. Then what do you get? Let me use the different color because the colors are exactly the same here. Okay, so then what do you get? 1 minus J omega divided by, help me here, 1 plus omega squared. So then what is the real part? Real part is 1 over 1 plus, oops, I have to do the, yeah, that's right. So 1 over omega squared, real part. Then what is imaginary part? Omega over 1 plus omega squared. Now J is on the top. Look at that. This is A plus BJ now. That's how you have to do that now, okay? So that's what you do here. Now, if you do that and plug in the value of omega, what is omega? 0. Start with 0 for now. Omega is 0. What do you get here? This guy is 1. This guy is 1. When omega is 0, this guy is 0. This part is 0. Then similarly, plug in the value of omega equals 0.1. Then you do the calculation. Then you get this. Guys, question here so far. Guys, give me 2 minutes, okay? It doesn't take more than 2 minutes now. So far, so good.
Yeah.
Okay. Now, similarly, I chose a random value of omega equals 0.5 and plug in here 0.5 square and stuff like that. Then I found the value to be this. And omega equals 1, I found the value to be this. Omega equals 2, I randomly chose the value of omega and up to 10. Then I make the table here. Omega equals 0, I get 1 plus 0j. 0, 1 plus 0j. 0.1, 0.99, you know, I just, summarize this, okay? Here. Let me bring this table to the other side also, here. Now I have this table ready, right? I have this table ready. Then let's do the plot. The plot is like this now, because my maximum value can go all the way to, what is the negative value can go up to? Negative value, maximum value is 0.5. I don't have to make more than 0.5 on the imaginary axis. This is imaginary. I don't have to make more than 0.5, negative 0.5. On the real axis, I can go as high as 1, right? Then all suddenly they are decreasing here. That's why on the real axis, my point is 1, maximum is 1. Imaginary, negative 0.5, real 1. Now let's plot it. So for omega equals 0, omega is 0, what is the plot? 1, 0, right? Real is 1, meaning come here, and imaginary 0. That's it. That's the omega equals 0. What is omega 0.1? 0.99. 0.99 is somewhere here, right? This is 0.99. Then what is the j? Negative 0.1. This is almost 0.1, right? This is what I have here, right there. This is my omega equals 0.1. How about omega 0.5? 0.8 means this guy in the real axis. Then what is the 0.4, right? Negative. That's 0.4. Look at that. This guy is this guy. Similarly, 1. Omega is 1, 0.5, 0.5. 0.5, 0.5, which is exactly here. This is omega equals 1. Similarly, omega equals 2 here. Then omega equals 10 here. Now, if you connect all those points, then what do you get? You get like this, right? This kind of plot is Nyquist diagram. They usually focus on positive values of omega. We just use positive, right? But the complete scale uses negative value of omega also. It will be, I don't know how it looks like. So you got the idea, right? Question here. Let me show you how do we do this in Octave, okay? Let me quickly show you how to do this in Octave. All right, so let me define I'm trying to do something like S plus 1, okay? Remember, let me do the S plus Bode plot for S plus 1. So first of all, you have to define sims S, right? That's sims S. Then define your transfer function. For S plus 1, how do you define transfer function? So this is how you define, okay? Let me show you how you define here. So what I did is this. So sims S, right? Not sysma. Sims S. Then next step, transfer function H equals TF. Transfer function of what? You have to have two things here. One is the denominator, the other one is, numerator. This is numerator, this is denominator. I'm doing S plus 1, right? My H is S plus 1. So it can be written as S plus 1 over 1. My denominator is 1. That's what it is. And in the numerator, you have 1 and 1, right? This guy is 1, this guy is 1. That's why 1, 1. That's what I did. Hope that makes sense. Okay. Then here, look at that. My transfer function is like this, right? This is s plus 1. If I do this, it gives me s plus 1. Look at that. Okay. This is how I represent my transfer function. Now, to find the Bode plot, remember s plus a. How does the Bode plot for s plus a look like? What is s plus a? Here, s plus a, right? My one is a is 1 here. The Bode plot should look like this or like this, right? It should look like this. Let's do the Octave and see what it does. So Bode, simply do Bode of what? H, because we already defined our H. Now, if you do that, then you will see the Bode plot. Ta-da! This is the magnitude, this is the phase. Okay. With that, I'm not, I was planning to do some, I couldn't do the stability and all those. How does this plot help, right? How does the Bode plot help to figure out the stability of the system, those kind of stuff? We couldn't do it. We tried our best. He's the Bode, he's the Bode, he's Bode, and he is Nyquist. Okay. So by the way, so we talked about root locus method, right? So that method is newer than the Nyquist and Bode. So that's why, even though even though this Bode and Nyquist are very nice method, but they are older than root locus method. So I don't worry too much about that because we already know the new method how it works, but we did not go in details in the Bode and the Nyquist. That's okay. All right. With this, I thank you so much, and the ball is in your court.
That's fantastic.